Welcome back to The Explainer. Today, we're diving deep into the earth beneath our feet to unlock some truly invisible properties, specifically the specific gravity of minerals. We're going to look at how two totally ingenious historical tools use just basic everyday physics to reveal a rock's internal density. It's actually pretty wild when you think about it.
So, how exactly do we measure the invisible properties of a mineral? I mean, you might naturally assume we'd need some super complex modern computers or lasers to figure out the internal density of a solid rock, right? But no way. We can actually solve this whole mystery using simple, elegant, centuries-old physical laws.
Okay, let's dive into this. Specific gravity, which you might also hear called relative density, is basically just a dimensionless ratio. It simply compares the weight of a solid sample out in the air to the weight of an exactly equal volume of a reference fluid, and usually that reference fluid is just pure water sitting right at 4 degrees Celsius.
Now, to really grasp the mechanics here, we have to anchor ourselves in Archimedes' principle. You've probably heard of this one. It's that foundational eureka concept stating that the buoyant force on an object submerged in a fluid is exactly equal to the weight of the fluid it displaces. This is absolutely crucial for understanding the difference between weighing a mineral out in the open air versus weighing it while it's completely submerged in water.
And that leads us perfectly to our base formula. Specific gravity equals the weight in air divided by the weight in air minus the weight in water. That denominator right there, the weight in air minus the weight in water, is literally the buoyant force described by Archimedes' principle. It's the physical manifestation of that displaced water we were just talking about.
All right, let's look at Section 1. Walker's Steelyard method, the balance of moments. So Walker's Steelyard is basically this classic lever system. Picture a long, graduated steel bar balancing on a pivot, or a fulcrum, with a heavy counterweight on one side. It completely relies on the principle of moments, where a moment equals force multiplied by distance. For this whole apparatus to reach perfect horizontal equilibrium, the total clockwise turning forces have to exactly balance out the total counterclockwise forces around that pivot. It's essentially a giant, very precise seesaw. Let's walk through the actual hands-on procedure because it's pretty clever. First, you suspend your mineral specimen from the long arm in the air, and you physically slide it along the beam until it perfectly balances horizontally. That exact distance from the pivot is your first measurement. Then, step 2, you submerge that very same specimen in a beaker of water and you slide it again to regain that perfect balance. Now, what's really interesting about this slide is how those physical sliding actions we just did map directly onto our variables. We'll call the distance where it balanced in the air variable A, and the distance where it balanced in the water variable B. We're literally taking real, physical space and translating it right into our scientific data.
Which brings us right to Walker's Steelyard formula. The specific gravity simply equals B divided by B minus A. Think about that for a second. The specific gravity is derived entirely from those linear beam distance measurements along the horizontal axis. It's just pure geometry and moments of force giving us the exact density ratio of the stone. How awesome is that?
Moving right along to Section 2, Joly's spring balance method, the tension of Hooke's law.
With Joly's apparatus, we're shifting our whole orientation. Instead of a horizontal beam, we've got a vertical stand holding a super delicate spiral spring. And because we're dealing with a spring now, our governing rule is Hooke's law. This law states that the extension of a spring is directly proportional to the applied force. So we're completely trading horizontal balance for vertical tension and elasticity. The procedure here is a really neat, highly systematic 3-step vertical process. First up, you record the initial index reading of the empty spring. That's your baseline. Let's call it x1. Second, you place the mineral in the upper pan, the one hanging in the air, and record how far this spring stretches down. That's x2. Finally, step 3, you move the specimen down to the lower pan, which is completely submerged in water, and record that new reading as x3. Basically, what we're finding is that the weight in air is proportional to x2 minus x1, and the weight in water is proportional to x3 minus x1.
So, the crucial point is how we're tracking the spring's elongation through these 3 exact points: empty, in the air, and in the water. By just looking at the stretch of the spring across these variables, the spring itself is doing all the heavy lifting to measure the force we need for our final calculation.
And here is where it all comes together with Joly's formula. Specific gravity equals x2 minus x1 divided by x2 minus x3. By just substituting those simple spring extensions right into the equation, we get a completely precise calculation of the specific gravity. It's such a brilliant, elegant application of Hooke's law to reveal the internal density of a solid object.
Okay, let's wrap this up in section 3, the weight of it all, synthesizing the science. And this brilliantly illustrates the two totally different mechanical approaches we've looked at today. On one hand, you've got Walker's Steelyard, operating entirely on a horizontal plane using physical levers and the principle of moments. On the other hand, you have Joly's balance, operating on the vertical plane using elastic springs and Hooke's law. Two completely different ways to manipulate basic physics.
But here is the real eureka moment, perfectly captured by this idea from our source material. Both methods rely on Archimedes' principle, weighing in air versus weighing in water to reveal hidden properties. That's the secret sauce. Despite totally different mechanics, levers versus springs, Archimedes' principle of buoyancy is the universal, foundational anchor for both of these tools. Displacing that water is the great equalizer, bridging the gap between horizontal moments and vertical tension.
Which really leaves us with this final, kind of mind-bending question. If basic physics can reveal a mineral's deepest, most invisible secrets just by measuring a few horizontal distances or how far a spring stretches, what other invisible forces are shaping the world around us, just waiting for the right tool to measure them? Think about that for sure the next time you pick up an ordinary stone. Thanks so much for joining me for this explainer. Keep exploring, and we'll see you next time.